Hey, I am Dani and today I will present about error in preliminary mathematics. This is a subject of numerical methods. And what is numerical methods? Numerical methods or numerical analysis is the approach of solving equations using computers. These are essentially trial and error process because the main objective of numerical analysis is to find approximate solution to complex problems. And the most of numerical solution methods results in errors in solutions because it's to approximate. So today we will understand why this happened and when this happened and how we can estimate the percentage or understand more about this. So in each problem, it's very important to keep track of the error made in order to be able to estimate the degree of approximation of the obtained solution. Because we want to know if my result is so far or is close of the real value that we are searching. So we have some errors. I will explain about two of the truncation errors are the result of later terms are often dropped into computations for the sake of computational efficiency, resulting in error in solution. And the other is most common is run-off. Errors happen because the computer uses only a finite number of digits represent the numbers and some calculus resulting in other um, numbers with more digits than are supported. This is okay, this is normal, this happen. So we understand the when. So here I put some numbers, some they are infinite, so the machine can't calculate and us too can't calculate with the infinite places of a number. And other case is because we have a lot of digits, but we will use a precision that is smaller than the number of digits in this number. So this will change a little the result, or a lot, depends of how much we are changing our values or when. So we can measure the error of two ways. We have the absolute error that is just a difference of the real value and the approximate value, and the other is relative value that is a percentage of the error difference. So go to examples. Today I will show three examples of how calculate absolute and relative errors. So in this first, I have 1.55 using 1 to precision. And my x value is 1.55 infinite fives. And if I go around this using 1 for precision, I will get number 1. But I have 5. That is a number that I will around to floor, to cell. So I will make it number 2, my x approximate value. So my formula say that we will make the difference using modulo. So I will put in the formula and we will find 0.00 if we calculate this difference with infinite for. And to find the relative error of this same example, we will consider the 0.44 infinite 4 that was our result in absolute error, and we will do the division using 2 that is our approximate value. So this will result in 0.22, and we can read this of the other way. So we can read this like 22% because we can multiply by 100 and read it like a percentage. This could be imagine it like a rule of 3. If you think a rule of 3 is easily or simple, you can calculate it using rule of 3. So the second example, I have a p number So 1, 4, 1, 2, 4, 2, 1, 3, 5. With 4 to precision, we will consider just the 4 number significatives. So I have 1.414, and like the number after 4 is smaller than 5, we will around to floor, not to cell. So it's just make the difference. So I will put the x value down the approximate value and make the difference. This is a red is a number positive, but we always consider this is the modulus. So ever will do a positive result, and we could read this like 2 multiplied by 10 uh, in exponent minus -3. Also, we have the relative error. So we consider the same values, and we will calculate the division of the approximate value and the absolute error. So we put in the formula. We can't forget that put in the model because could be a negative value, and this will result in 0.0015090. And also we can write this like 1.1599 multiplied by 10 in the exponent -4. And the last example, and example 3, is which is a number smaller than 0, because I think is very important. Think the difference about this, because we will not count 0 um, left 0 like a significant figure, because we will start in 7 because it's the first significant value. So if I will use in precision to 2, we will consider 0.075, because 75 is our part significant, the first 2 digits significant. So when we are around this, we'll pass the 5 to 6, because 9 is higher than 5, and this make we increment in this value. So if we calculate the difference, we will find 0.000545, and here we have an example that is negative, so we can't forget the model, and this will make it, we have it the same value but positive. Also we can read this like 4.5 multiplied by 10 in exponent -5. And if you will think this like a percentage, you will see that is a very slow percentage. And the relative error, we have the division of these two values. We can read like 0.005921 and other, etc. Also, we can write like in multiply by 10. And my favorite part now, the algorithm. We can write our algorithm for this because we always make the same thing, so have a pattern in this. But also, I said in the start of this video, computer could make little errors with a lot of places. So we can check our answers, but if you want a high precision, take care. So for this algorithm, I have in line 29 the call of the error using our error method, using our numbers of our first example, and this is 1.555 using precision to 1. So when I get here in line 17, the method will pass these patterns, and the first thing that we will do is round the number. So we go to method round significant, pass the same values, and if the number will be equal to 0 or slow, because when I pass to int, if it's 0.001, this will make true. So to around this, using the Python method, because this is Python round will consider that you are passing a number and the number of places that you want to round. So if I have 0.0076 that I want around using 2 to significative, if I pass 2 to the method, they will just return 0.00. Is not what we want. We want the real significative values. So we will have our variable significative minus the log of the our number in log of 10. This will return the number of places that are distance of the 0. So if I have 0.001, we will return 3, negative 3. And when I calculate this significant value minus negative 3, I have a positive 3 plus the significant values. So I will find the round value considering the significant figures. Else, if you are a number higher than 1, higher than 0, like 1.5, or the other that you will use 1.4 or 2, 10, etc., we will do the same thing with log, but this log will result in a positive number, and we will decrement one of this value because um, like I said, the round method of Python will consider that we are passing the number of places to the right of the dot. So if I pass 1 to significant value and I am passing the number 9.1, I just want 9. So if I pass 1 to this, they will return 9.1. So I will decrement this to they return the right value that I want. So when I come back of the method, I will have the rounded value, and I already can calculate my absolute error, that is the model. In Python, model will appear like ABS, absolute value, that is number, minus the rounded value like we do in the examples before. And to calculate the relative error, we will do the absolute error division to absolute or model of rounded value. So to this we have all of things that we want, and we can check if our calculates have get a right value. This is amazing, and this is this for today. So if you like this video, make your like, share with your friends, and comment your suggestions. Thank you. Bye bye.